Let's learn how to find the derivative of a function from first principles. This process is also known as finding the derivative from definition. Let's start by visualizing what a derivative means geometrically. Consider a function f of x. When we talk about its derivative at a point, we're really talking about the slope of the tangent line at that point. To find the slope, we follow three key steps. Step 1. We take a point x and another point a small distance h away from it, which we call x plus h. Let's mark these points on our curve. Step 2. We find the change in y divided by the change in x between these points. This gives us the slope of the secant line. Step 3. We then let h approach 0. This means we're letting our second point get closer and closer to our first point. As h approaches 0, our secant line becomes the tangent line. Exactly what we wanted. Let's summarize the steps. First, we substitute x plus h for x in our function to get f of x plus h. Then we subtract f of x and divide by h. Finally, we take the limit as h approaches 0. This gives us the derivative formula from first principles. This definition is fundamental to calculus and gives us a precise way to find instantaneous rates of change for any function. Let's understand how to find the derivative of x raised to the power n using the first principles definition of derivatives. Let's start by defining our function. Let f of x equal x to the power n. Therefore, when we increment x by h, f of x plus h equals x plus h to the power n. Now, let's recall the definition of derivative. The derivative of f of x is equal to the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. Substituting our function, we get the derivative of x to the n equals the limit as h approaches 0 of x plus h to the n minus x to the n, all divided by h. Here's where we use a clever algebraic trick. We can factor out x to the n from the numerator by writing x plus h as x times 1 plus h over x to the power n minus x to the n. Now, we can use the binomial theorem to expand 1 plus h over x to the n. The binomial theorem tells us that 1 plus x to the n equals 1 plus nx plus n times n minus 1 over 2 factorial times x squared, plus higher order terms. Applying this expansion to our limit, we get x to the n times 1 plus nh over x plus n times n minus 1 over 2 factorial times h squared over x squared, plus higher order terms minus x to the n, all divided by h. Simplifying the numerator, we get x to the n times nh over x plus n times n minus 1 over 2 factorial times h squared over x squared plus higher order terms, all divided by h. When we distribute x to the n over h, we get nx to the n minus 1 plus n times n minus 1 over 2 factorial times x to the n minus 2 times h plus higher order terms. Finally, as h approaches 0, all terms containing h go to 0, leaving us with just nx to the n minus 1. This is the power rule for derivatives. This proof shows us why when we differentiate x to any power n, we multiply by the power and reduce the exponent by 1. It's a direct result of using the limit definition of derivatives combined with the binomial theorem